Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Cagney, and Peter Galvin, published by Wiley Publishing. We finished the last lesson on multi-core scheduling, and now we're going to move on to heterogeneous multiprocessing systems.
In the examples we've discussed so far, all processors are identical in terms of their capabilities, therefore allowing any thread to run on any processing core. The only difference being that memory access time may vary based upon load balancing and processor affinity policies, as well as on NUMA systems. Although mobile systems now include multi-core architectures, some systems are now designed using cores that run the same instruction set, yet vary in terms of their clock speed and power management, including the ability to adjust power consumption of a core to the point of idling the core. Such systems are known as heterogeneous multiprocessing. Note this is not a form of asymmetric multiprocessing as described earlier, since both the system and the user tasks can run on any core. Rather, the intention behind heterogeneous multiprocessing is to better manage power consumption by assigning tasks to certain cores based upon specific demands of the task. For ARM processors that support it, this type of architecture is known as big dot little, where higher performance big cores are combined with energy efficient little cores. ARM, previously referred to as Advanced RISC Machine, originally Acorn RISC Machine, is a family of reduced instruction set architectures for computer processors, configured for various environments. Using big dot little architecture, big cores consume greater energy and therefore should only be used for short periods of time. Likewise, little cores use less energy and can therefore be used for longer periods. There are several advantages to this approach. By combining several slower cores with faster ones, a CPU scheduler can assign tasks that do not require high performance but may need to run for longer periods, such as background tasks to little cores, thereby helping to preserve battery charge. Similarly, interactive applications which require more horsepower but may run for shorter durations can be assigned to big cores. Additionally, if the mobile device is in power-saving mode, energy-intensive big cores can be disabled and the system can rely solely on energy-efficient little cores. Windows 10 supports heterogeneous multiprocessing scheduling by allowing a thread to select a scheduling policy that best supports its power management demands. Your authors have included several sections on specifics of common operating systems, Linux, Unix, Windows, and Solaris. If you're interested in exploring a particular operating system, you're encouraged to examine those sections. So in summary, we have learned that CPU scheduling is the task of selecting a waiting process from the ready queue and allocating the CPU to it. This is the responsibility of the process management system of the operating system, or the process manager if you prefer. The CPU is allocated to the selected process by the dispatcher in the Windows operating system. Scheduling algorithms may be either preemptive, where the CPU can be taken away from the process, or non-preemptive, where a process must voluntarily relinquish control of the CPU. Almost all modern operating systems are preemptive. Scheduling algorithms can be evaluated according to the following 5 criteria: CPU utilization, throughput, turnaround time, waiting time, and response time. As we have already discovered, these criteria often conflict, so the challenge is to strike a balance that will best serve the system. First come, first served scheduling is the simplest scheduling algorithm, but it can cause short processes to wait for very long processes. Shortest job first scheduling is an improvement, providing the shortest average waiting time. Implementing shortest job first scheduling is difficult, however, because predicting the length of the next CPU burst is difficult. Also, in a preemptive environment, it may cause long jobs to remain idle and require a method of aging to get them out of the system. Round-robin scheduling allocates the CPU to each process for a specific period of time, called a time quantum or a time slice. If the process does not relinquish control of the CPU before its time quantum expires, the process is preempted and another process is scheduled to run for a time quantum. Priority scheduling assigns each process a priority, and the CPU is allocated to the process with the highest priority. Processes with the same priority can be scheduled in first come, first served order or using round-robin scheduling. Multi-level queue scheduling partitions processes into several separate queues arranged by priority, and the scheduler executes the processes in the highest priority queue before moving to the next queue. Different scheduling algorithms may be used in each queue. Multi-level feedback queues are like multi-level queues, except that a process may migrate between different queues. This allows for several advantages, such as allowing a process's behavior to be rewarded by moving up in queues and offering a method of aging. So, how does a process lose the CPU? First, it can do it by voluntarily giving it up when finished to terminate. It can also move to another wait queue for an input-output device. Or it can be forcibly removed because its time quantum has expired. Multiple core processors place one or more CPUs on the same physical chip. Each CPU may have more than one hardware thread. From the perspective of the operating system, each hardware thread appears to be a logical CPU. Load balancing on multi-core systems equalizes the load between cores, although migrating threads between cores to balance loads may invalidate cache contents and therefore may increase memory access times. So there you have it. There's our discussion of the process management system. This was a pretty good chapter. It was somewhat lengthy, but there was a lot of good information. Go over your notes, take care of whatever business you may have, and when you're ready, we will move on to the next management system of the operating system.